Okay, so this begins the first video set for the third portfolio test, essentially modeling using functions. And we can't really describe a model of a function without going into a little bit the definition of a relation and then a function and what it's all about. A relation is basically two or more variables that have a relationship with each other. An example would be, as you age more, your height increases. So changing of your age, the changing of your height, these are two variables that interact with each other. That's a relation. Both of these are a function, an example of a function as well too, because they have something called one-to-one correspondence. And what that means is that the independent variable, or the input, is a non-repeating quantity. It's only matched with one value of the output. One-to-one correspondence. So for every input, there's just one output. We see the function in the table on the left here. All of these numbers in here, right? -1 just maps to 3, -2 just maps to 5, -3 to 3, and -5 to -3. This is one-to-one correspondence. All of these independent variables, the x column on the left, just map to one value. But if we look at the function table on the right, this input value of the independent variable 3 matches with 2. So -1 and -3 output variables. That's why that's not a function. So we'll see representations of a table like this a bunch through this unit. These are the two tables from the previous slide. We'll also see representations of functions as a graph, as an equation. We can convert these equations later on into function notation, which we'll see in a moment. But essentially, this linear line is a function because all of these x values, like -1 right here, matches with one singular output value. But in the not a function, this circle here, look at x is equal to 0. It matches with 5 and -5. That's not going to work. A circle is not a function. So this is the equation of that circle. This is the equation of that line. These are representations which are not functions. On the top, representations which are functions. Function notation. Here's where we get into more of the meat of the matter for the actual portfolio test itself. Function notation is just a notation. It's a way for mathematicians to understand certain concepts in math and sort of a shorthand to rewrite it. It's just the way you visually present a mathematical concept. In this case, we're presenting the equation of a function using function notation. So there's two major or a couple of major identifiers in the actual notation itself. This is read f of x. It's not multiplication. It's not f times x. This is the full representation of the dependent variable on the left-hand side of the equation. The independent variable is represented inside these parentheses. In this case, it's x. And then the letter that's outside of the parentheses here, that's called the name of the function. The most common function name is f. Another thing we can understand from function notation, if we have an actual value or an element of the domain, it's called an actual value of the function f, we know that that function's input value is also inside these parentheses here. So the input value is inside the parentheses on the left. And then the output value is plug in for 5 into this function here, is represented by this whole numerical expression, 3 times 5 plus 1. So we can see very easily the independent variable, the dependent variable, the input value, and the output value given function notation. So these are some of the advantages of function notation, some of which we've already gone into. Function notation allows for you to look at different functions on a page and quickly name them. You don't want to say, oh, y is equal to x plus 1, y is equal to x plus 2, y is equal to 5x minus 3. That's just, it's too much to say for mathematicians as an equation. So you can say, this is f, that is g, this is h, this is capital S, this is the absolute value function, this is the George function. It's a way for you to have a collection of objects and just name them easily. So that's one advantage. Second advantage, we can quickly identify the independent variable in the problem, or the input value as well. That's always going to be what's inside the parentheses. So you don't necessarily have and know exactly what what the independent variable is if an equation's not in function notation. 3. It quickly states the element of the function to be examined. So that's the input value. So you can quickly say, okay, f of 5, well, what does this mean? What does it say? It means evaluate this function, 4x is equal to 5, plug it into the right-hand side of the function, and get the output. All right, we'll see that more in a moment in the next slide. Something to keep in mind, these are two equivalent notations. Slope-intercept form on the top, function notation on the bottom. They mean the same thing. Y and f of x are interchangeable. Okay, so let's start by evaluating a function. These are the extra skills that I want you to do in this section. So you're given this function, y is equal to, or f of x is equal to 3x plus 5. Find f of 4. Okay. So you saw a little bit of this in the last slide, but essentially what you're doing is you are, oops, not f of x, sorry, you're replacing x with 5 or with 4 for f of 4, and then on the right-hand side, you're just replacing x with 4 here, 3 times 4 plus 5, and then evaluating this right-hand side. 3 times 4, what's that? 12 plus 5, and then 12 plus 5 is 17. Okay. So what does this mean? This means that when the input is 4, the output is 17. So we can write this as a table of x and f of x. This is the coordinate point for 17. So you can write this also as a coordinate point. 4. And then that is a comma. 417. So you show the evaluation of this function f of x at 4 as a final answer like this. It's saying f of 4 is equal to 17. This is my final answer. You can think about this as a coordinate point, as we wrote on the right there. F of 4 is equal to 17, input 4, output 17. Evaluating a function. Next thing we want to do is be able to graph a function. So we graph functions, or equations, I should say, in slope-intercept form in topic 1.3 earlier in the school year. But we were dealing a lot in the space of from x from negative 10 to 10 and y from negative 10 to 10. Here, when we're modeling, we want to go towards higher magnitude values of the slope and the y-intercept. So what would we do? Same thing, we got to figure out first how we're going to graph the y-intercept. We start in the same place. So what's a scale that would make sense fitting in this y-axis here? So you're thinking about a scale that you might want to use. 25, how about going by 5s? All right, 5, 10, 15, 20, 25. I'll just use the same uniform scale here on the x-axis. So let's start out by graphing this coordinate point here. Come on, we're graphing the coordinate point. All right, at 0, 25, the y-intercept, right. Okay, now I'm going to introduce something new. We learn how to evaluate a function notation here. Okay, well, I want to be able to graph the next, at 5. I use the same scale here, the next grid line over on the right. So what I can do is evaluate f of 5. Get my 5 right here. Okay, so in this case, f of 5 is 15 times 5 plus 25. 15 times 5, that's 75. Still adding 25. 75 plus 25 is 100. So I'm going to write that in. Okay. So what did we do? we discovered the coordinate point on this function, 5, comma, 100. It's the next one over in the grid line. So that means that I'm going to then have my coordinate point here. And wait! Hold on. This is not 100. This is going by 5s. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. This is not going to fit. We can't fit this scale going by 5. Sure, you can graph this off the graph, but we've discussed and not do that before. That's not a correct representation of the scale. Here's something else that we could do. All right. The only change I'm going to make here is the scaling of the y-axis, going from 5 to 10. We're still going to graph our first coordinate point here. At 0, 25. I'm keeping my same work over here, which we just found out f of 5 is 100, the coordinate point 5, 100. But here we can graph if we go by tens. 60, 70, 80, 90, 100. The coordinate point 5, 25. That is a coordinate point which is on this graph. And now we can graph this line. So what we did is we ran into an issue in this last one. We said, okay, well, we're using this scale. We have the coordinate point 5, 100. 100 is all the way up here. I can't graph that if I'm going on a uniform scale of by 5s along y, by 5s along x. That's not going to work. What I need is a different scale and changing my scale on the y-axis. So you might want to get out your pencil when you're doing work like this. You might be changing the scale depending on what your graph looks like to make it intelligible. Here's the last option that you could do as well too. Keep in mind that this slope here is 15 over 1. We can use the exact same scale, or we can use, a scale which is more representation of the left to right movement, meaning up 15, right 1, along x. If I go by 1s here, it's okay to have this scale going by 5s and then this scale by 1s. As long as it's uniform across x, uniform across y, you're good. Now here, I can graph according to that exact same method that we used in topic 1.3 as I detailed here. I start at 25, I go up 15, keeping in mind that this scale along y is by 5s. 5, 10, 15, right 1. That's the second coordinate point on my line. Use my ruler, graph and draw the line straight through. So really, the second coordinate point that we found here is 1, right? 30, 35, 40, 40. So I use the coordinate point 0, 25, and I use the coordinate point 140. And I graphed using the method that we knew. So both this method here, which I just detailed, and then the last slide, where all I did was just increase the scale on the y-axis, you have both of those methods at your disposal. Remember, do some playing around and changing with the scale in order to make your graph fit and make it work and make it intelligible. Sometimes graphs are too steep, the line is too steep, and it's sort of hard to read. As long as the graph is accurate, the scale is uniform, and the coordinate points are correct, I don't care if the line is too steep. I'm just sort of giving you multiple avenues here, going up, down, left, right from 25, up 15 and right 1, or this avenue, starting at 25 and then evaluating the function at 5, 100 and being able to graph that output value of 100 by changing the scale along the y-axis. So there you go. Graphing functions, evaluating functions.